Thanks a lot. First of all, just let me thank the organizers for giving me an opportunity to tell you about the work I've been doing. Just a caveat, my own background is actually in sort of non-equilibrium thermodynamics, many-body physics. And in recent years, I've been dabbling a little bit in quantum simulation. So I'm based in Trinity College, Dublin. For those of you who maybe haven't visited in an academic capacity, if you visited as a tourist, I'm sure you've walked through it. It's really in the center point of Dublin. You might have gone to our old library that hosts the Book of Kells, which is a major tourist attraction. And what I was going to say is that in the last couple of years, we've been doing a lot of work in Dublin to try to, let's say, advance research in the quantum domain. So we have a little institute called the Trinity Quantum Alliance, which is built with a bunch of different corporate partners that are based in Dublin and a few startups. And I just want to say that if you want to visit, please drop me a mail. We have a visitor's budget if that interests you. OK, so what I want to talk about today is a project that was done in collaboration with a startup based in Finland, a software startup called Algorithmic. They're a startup that's typically focused on developing quantum software for the life sciences, but they also develop a lot of sort of, let's say, enabling software like error mitigation strategies, et cetera. And also with IBM, we actually have a collaboration that involved the IBM teams in Zurich, here in Yorktown, and also in Dublin. And the kind of idea was to simulate something interesting on their superconducting devices at sort of utility scale, so large simulation of something that's kind of relevant in current many-body physics. So the title of the paper that's currently on the archive, I hope it will be published soon, is Dynamical Simulation of Many-Body Quantum Chaos. So again, a kind of disclaimer on many-body quantum chaos. It's how you define it is still very much an evolving topic. Obviously, quantum chaos was developed in the 80s, in the 70s, et cetera, typically kind of focusing on single particle systems. But many-body quantum chaos is typically a collection of phenomenology. And roughly speaking, you can see it as being spectral statistics of systems which are kind of local, but share that in common with random matrices. You can see it like this. But it's a disclaimer that it's not fully developed, I would say, as a theory yet. OK, so the people involved, I can't name them all. Often with these kind of large-scale works, there's a bunch of different moving pieces. But in particular, I'd like to highlight the work of Matea Lee and Lauren Fisher, who did a lot of the heavy lifting in terms of running codes, error mitigation, et cetera. My own role is more on the sort of physics side, and that's what I'll focus on today, tell you about why it's exciting, tell you a little bit about the theory behind it, et cetera. And I should also mention Sergei Filippov, who is probably the one person in the group that understands every part of this moving piece. OK, so what I'll talk about, I'll give a motivation, and then I will kind of move on and tell you a little bit about dual unitary circuits. And in particular, I'll tell you why I find personally dual unitary circuits to be very interesting from a many-body perspective, and then give you a little bit of details and show you some results on the experiment/simulation of measuring correlation functions and decay of the autocorrelation functions in the model. OK, so a motivation would come, say, from, we know that there's these fabulous sort of experiments in analog quantum simulation that have been going on for a number of decades now. And really, what's really, let's say, amazing about these experiments is that they allow you to sort of do control of many-body systems at timescales which would be kind of unprecedented in condensed matter physics, right? And if you ask maybe theorists, what is one of the fundamental things we've learned in theoretical physics from this sort of generation of experiments, to the top of many people's lists would be, well, we've really refined our understanding of how closed quantum systems thermalize, right? So there's a number of experiments that I highlight here, but there's a whole bunch of them I could have highlighted, right? Furthermore, I would say what it's done is that it's refined our understanding of how and when thermalization breaks down. So there's a number of different instances that have been mentioned already in this workshop, ranging from localization to integrability to weak ergodicity breaking we heard about, so scars and fragmentation, et cetera. And even, we've heard about more generalized concepts of thermalization, so-called deep thermalization, et cetera, where higher order correlation functions also thermalize. I mean, this experiment probably started it all off. It's already almost 20 years old, and it was an experiment basically that simulated a Lieb-Liniger model, which is an integrable model. The system doesn't thermalize, but it thermalizes to a generalized Gibbs ensemble, and many, many results have followed after that. So just to put us on the same footing, what do I mean when I talk about thermalization in an isolated quantum system? So imagine I have some Hamiltonian. That Hamiltonian is not special. There's no conserved quantities, only the Hamiltonian itself. You can have global conserved quantities, but no local ones, okay? Imagine it has spectral statistics akin to a random matrix, but it's not a random matrix itself, and it's large, okay? So a reasonable assumption is you take an initial state that's not an eigenstate. It's a superposition in the energy eigenbasis. And that state will have an extensive energy and sub-extensive energy fluctuations, so that its distribution of energy is sharply peaked about the average value in the thermodynamic limit, right? It's a sort of reasonable statistical assumption. And now we do time evolution. That time evolution could be, sort of a quench evolution. It could be a systematic preparation of that initial non-eigenstate. And we let the system run, and then we look at an observable, right? So if you look at a kind of generic expectation value of the observable, expand it out into the energy eigenbasis, separate out the terms into diagonal and off-diagonal components, you see the off-diagonal components, sort of carry the phases between different energy eigenstates, and the system starts to equilibrate towards its time average value, okay? So if I take a time average of that signal, I see that I wash away the phases, assuming that I have no degeneracies in the Hamiltonian, and then I essentially go towards an expectation value in this ensemble, which is called the diagonal ensemble, which is an ensemble that's diagonal in the energy eigenbasis and whose energy eigenvalues are the overlaps of the state with the energy eigenbasis, okay? And the question of thermalization is just this. It's when can I safely replace the expectation value in the diagonal ensemble with that of a statistical ensemble like the microcanonical ensemble at energy E, where that energy E dictates the thermalization temperature and it's set by the energy density of the initial condition, okay? So this is what I mean by thermalization. We know that the answer to this, okay, is that the system fulfills the ETH ansatz, right? So that's just an ansatz on how the matrix elements of the observable behave in the energy eigenbasis. And actually, all you need to do for this expectation value equivalence to occur is you need the diagonal matrix elements to become a smooth function of the energy. This allows you to Taylor expander out the average energy, and you can show that this is equivalent to microcanonical thermalization. What's important for this talk is that also the off-diagonal matrix elements of the observable in the energy eigenbasis are exponentially small. Okay, you see that there's a term in the exponential of the thermodynamic entropy, which is extensive. But not only that, these small off-diagonal matrix elements, they encode important features connected to the autocorrelation function of that observable. So not only does it dictate observable thermalization, something that's often forgotten about ETH, is that it also dictates that the autocorrelation functions, when they're Fourier transformed into frequency space, fulfill the fluctuation dissipation theorem. So fluctuations are also thermal, okay? So ETH mandates both observables and two-point functions, and it doesn't describe correlations beyond 2 point, right? You need something more generalized than that, okay? Because there can be correlations between different matrix elements. It's another story. Okay, so that's for continuous time evolution. And the point that I really want to get across in this talk is that discrete is different. So we saw this very nice talk on Monday by Continuum on their recent work, which looked at exploring sort of thermalization dynamics as you vary the Trotter step when you're trying to simulate a continuous time dynamics. And they show that there is some time scale, okay, which is exponential in the inverse of the Trotter step, after which the system feels its discreteness and just heats up to infinite temperature, okay, because time translational symmetry is broken. And they use this as a basis for something that's hard to classically simulate, but also it highlights that when you discretize a system, you have to be careful and things get very different. I also point out a very nice recent paper by Marcos Niderich, who analyzes this very carefully at the level of autocorrelation functions and even uses this pre-thermalization plateau as a simulation tool to extract the fusion coefficients of the underlying sort of continuous time model. Now, you can Now what you can do, okay, is you say, I don't really care about continuous time evolution at all, but I want to do many-body physics really at the level of completely discretized system. So I give up energy conservation from the start, and I just think about building phases of matter from the stroboscopic evolution of 2-qubit gates kind of layered like this in the following picture. And what I would argue is that in this context, which is rather minimalistic, you have all of the same features of unexplored universal and emergent phases that you typically get in the continuous time analog when you have time translational symmetry and a valid Hamiltonian. So I'm going to specifically focus on this talk on brickwork circuits where you layer layers of 2-qubit gates on even and odd qubits. And this is like a Floquet, discrete Floquet evolution. So now you don't have a Hamiltonian, but you have a Floquet unitary, which is basically repeated on unit cells. Okay? So now if you want the spectral information about your system is encoded in the spectrum of the unitary, which is of course complex and bounded on the unit circle. Okay? And many of the same things that we discuss for Hamiltonian systems can be done at the level of these guys. So what sort of things can you do? Well, as a theorist, or if you're interested in numerics, you can now start playing a lot of games. I'm not talking about kind of random circuits. I'm really talking about putting in specific 2-qubit gates into my brickwork circuit. And the class of 2-qubit gates is completely characterized by U2 here. So U1, U2, V1, V2. These are just elements of SU2. And the G operator encodes the sort of interactions. You see it's kind of got a Heisenberg-like form, okay? And then you can start playing games with the different coefficients of this 2-qubit gate, and you see you get swap, you get dual unitary, which I'll come to in a second, C0, and a wide range of interesting phenomena, which I would argue has even been rather unexplored, right? From the perspective of many-body physics. We haven't fully characterized all the phases that emerge in the large N limit when you start playing games like this, right? So I'm really talking about a discretized version of, let's say, the traditional condensed matter. So just to give you an example, you can take this extreme case where you force the system to have an extensive set of locally conserved quantities and to be integrable. Okay, this is what I mean. It has Poissonian level spacing, statistics, solvability, etc. And if you look in the literature, you can find examples of things which appear in such circuits which have recently been characterized, which don't actually have an analog in the continuous time setting, right? So the first time I was convinced that there's something interesting to be explored for doing physics like this, my student, Nathan Keenan, who's actually also an employee of IBM, we have this program in Dublin, came to me and we said, okay, let's start looking at simulating the physics, okay, of a discrete time XXZ model, okay, which is just, the XXZ model is the standard Heisenberg model. It's been beaten to death for 100 years by theorists. And its high temperature transport super well characterized. It conserves magnetization. And what we did on one of the older, say smaller scale IBM machines is we started to propagate initial density inhomogeneities and track, if you want, this inhomogeneity as a function of time and look for sort of universal transport exponents which are predicted from theory. So I don't want to get into the details of this thing, but just to say there are regions of the discretized model in the phase diagram which are different from the continuous model. For example, you get whole lines as opposed to points, which indicate the so-called super diffusive Cardar-Parisi-Zhang scaling. And I was kind of shocked to see this famous universal parameter appearing already at a very small scale simulation. A very similar experiment, but I would say much more comprehensive and at larger scale, was performed by Google last year, who also noticed that you could really look for these sort of universal exponents in the transport phase diagram of the XXZ. So what they do in this experiment is they propagate domain walls and they look for magnetization transfer as a function of time and then look for the exponents in the transferred magnetization. So you see on the right-hand side different regimes corresponding to theoretical predictions, ballistic, diffusive, and super diffusive. Okay, so integrable circuits, these are something which are very interesting to be built in this picture of brickwork circuits, right? Now, how about something that's in between a random circuit and in between an integrable circuit? So you want to think about ergodic circuits, right? Is there a notion of eigenstate terminalization hypothesis at the level of a circuit? And you say, well, hold on a second. It's a kind of trivial thing because don't circuits that are non-time translationally invariant heat up to infinite temperature? And that's true. So if you look at the matrix elements of an observable now in the Floquet eigenbasis, what you see is that indeed the diagonal matrix elements give the infinite temperature prediction for the observable, but you still have off-diagonal matrix elements which are exponentially small in the system size, okay, and which encode important information regarding the autocorrelation function, okay? So on the right-hand side, you see this f function. Notice that it doesn't depend on the energy, namely the temperature anymore, because everything's at infinite temperature. And the correlation function of relevance in this circuit is the infinite temperature autocorrelation function, and that will be the central object for simulation in the experiment that I'm going to show, okay? So so what circuits am I interested in? So going back to this sort of brickwork setting, okay, in my brickwork setting now I'm choosing gates which are so-called dual unitary gates. I guess many of you have heard about them before, but essentially it's very simple. Take a bipartite unitary, okay, write it in this sort of tensorial way where you have input indices and output indices on the top right-hand side, okay, and now you're going to reorder the indices so that the inputs now run left and outputs on the right, and if the resulting operator is still unitary, you say this is a dual unitary, okay? So it's a unitary which is symmetric in both space and time, okay? It has this nice symmetry. This is what a dual unitary is. So some examples of dual unitaries. A swap is a clear example. It's something that's symmetric in space and time. It's unitary in both directions. An identity, it's not dual unitary, okay? You can see this from its tensor representation. And neither is a product of unitaries. These are not dual unitaries. For qubits, the class of dual unitary gates are fully characterized, okay? So if you go back to this picture of U2 being the general way of writing down a 2-qubit gate, what you have is that all the dual unitary gates are in this 14-parameter subspace of the otherwise 16-parameter unitary, okay? So you fix 2 parameters of a unitary, and then you have a full dual unitary kind of thing. Okay, so a dual unitary circuit then, of course, is just a brickwork circuit composed of dual unitary gates, right? So it's unitary, this whole circuit is unitary in both the temporal and the spatial direction. So what about the properties? So just to list a few of them, and this is kind of theory work that's been done over the last 5 years. So there's very nice results by Tomasz Prozen's group, by Sirac, et cetera, that show that dual unitary circuits give the fastest possible entanglement growth starting from certain initial states, like product states, okay? Fastest possible. There's a converse kind of result which shows that if you have a local circuit that has really fast entanglement growth, then it must be dual unitary, okay? What else? So they also spread correlations in the fastest possible way. So now if you think about how, sort of causality and locality bound correlations, of course there's a light cone structure in the temporal direction, but now because of this dual unitary feature, okay, you have also got a light cone in the spatial direction, right? So you have a light cone going in this direction as well. And remarkably, as shown by Bruno and Tomasz and Pavel, the correlation function itself only is non-zero on the light cone, okay? That doesn't mean it's fixed on the light cone, but it can decay on the light cone. It doesn't live inside the light cone, right? So it's really spreading correlations really rapidly. And this is precisely what we want to try to measure in the experiment, okay? So I should also point out, it's a bit technical, I don't want to get into it, but the exact value of this correlation function, its exact decay form on the light cone can be computed analytically. These circuits are not integrable and they're not Clifford, and I would say it's an extremely rare example of an exact result in the thermodynamic limit of a quantum many-body chaotic system, okay, for correlation functions. This is why they're kind of very interesting for theorists. So just to recap, again, circuits, they're both unitary in space and time. They have solvable features. They're not necessarily integrable, not necessarily Clifford. They're highly chaotic, scrambling and entangling, and fully characterized in terms of their 2-qubit representations, right? So it makes them ideal for benchmarking if you have a non-Clifford circuit that has a dual unitary point and you simulate a correlation function, then you actually have an analytic result to compare against, right? I should also say they can't be localized. This is another result. We've done some work to show that they can display weak ergodicity breaking. I thought about putting it into the talk, but I already realized I'm running out of time. But just to highlight the work that we did, we embedded so-called many-body scars within this circuit. I hadn't seen this done in non-continuous time models. This is work we did with Silvia Pappalardi in Cologne last year. Okay, so what model am I interested in for simulation purposes? This was mentioned, I think, in a talk on Tuesday. So I'm going to look at the Kick-Deasing model. Kick-Deasing model was is a paradigmatic model to study many-body chaos in. It's like you see a bog standard sort of classical easing model, and then you have a kick in the longitudinal direction, which is just a sum of x gates. And then, you can think about this thing as being a trivial easing model, which is perturbed at integer times by a field in the longitudinal direction, okay? How does this transpile on hardware? It's actually very good for the native, say, superconducting hardware. You can take each of these 2-qubit gates and split it up into 4 single-qubit operations and 2 entangling gates, okay? So what's known about this model in the context of dual unitarity is that it has this nice dual unitary line, okay? So just take a look at the model. Of course, when either h or b is 0, model is fairly trivial. So for example, if h is 0, you're left with something which is mappable to free fermions. If b is 0, then you have something which is almost classical, right? Is classical, right? But when j and b, the magnitudes of j and b are both equal to pi over 4, then you have this dual unitary property that I just described of the whole circuit being symmetric in space and time, okay? And not only that, when h is 0, okay, you have a dual unitary Clifford point, and when h is not 0, the circuit is non-Clifford but dual unitary, okay? So it has these points that we want to investigate. Right, and so what do we want? How do we measure something interesting, right? So the object that we're going to look at is a 2-point correlation function of Pauli x, okay? On an infinite temperature state. As we heard, this is the relevant sort of correlation function for understanding dynamics at the level of the circuit, because the identity is a natural fixed point, right? It turns out, that you can actually compute analytically the decay of this correlation function as a function of the transverse field h, right? So it's exponential, of course, in time. It's going to be exponential in time, decay exponentially, because this is a rapidly mixing circuit, right? How do we sort of do this? Well, I don't know, something that when I started out I wasn't aware of, but you might think, okay, 2-point correlation functions are hard, but at infinite temperature you can write any 2-point correlation function as an expectation value over a specially prepared initial state, right? It's pretty simple to see that. If you look, you just write down the expectation value of sigma x in this circuit. Okay, you choose this initial state, which is plus on 1 qubit, identity on the rest. Okay, if you go through this calculation, you see that this is actually formally equivalent to the sigma x correlation function, the autocorrelation function. So that's a consequence of infinite temperature. It doesn't work outside of infinite temperature. But you think, okay, I still have to sample over the identity, right? Which is a bit annoying. And it turns out there's a remarkable thing that you can do at the dual unitary point. So you can get rid of the identity on the n-1 qubits and swap in sort of Bell pairs, right? So you have plus now and you have a tensor product of Bell pairs. How do you see this working? Okay, is best if you kind of go to the tensor network-like picture. Okay, if it's not familiar, don't worry too much about it. So I mean, in this tensor network language, you can write the red blocks represent unitaries, the blue box represents adjoints, and you see up in the top right-hand corner the conditions for unitarity and dual unitarity are written in a kind of tensor way, right? So if I write down a correlation function on the top row here, it looks like this, right? This is what a correlation function looks like as a tensor network, and the Bell pairs act like hooks, okay? They act like hooks. So that combined with the unitarity property in the tensor network and the dual unitary property allow you to contract the tensor network representation of the correlation function so that everything only lies again in the light cone. So it's equivalent. And it actually only works for open boundary conditions, this trick. But it's great because you can now start off with an initial pure state, run your dynamical evolution, and hopefully measure something like autocorrelation function decay. Okay, this is the goal, and this is what we did. Okay, so now for some results. Okay, so we performed, in Abhinav Kandala's group here in IBM Yorktown, they performed a very large simulation of the dual unitary circuit representation of the self-dual easing model, okay, on their previous generation of chip, which is the IBM Strasbourg. It's a 127 qubit chip. So we were able to sort of simulate the system up to 91 qubits and involved 4,000, sort of roughly 4,000 entangling gates. And so the plot here on the right-hand side is this autocorrelation function, okay, on unmitigated data, just to show you that you get roughly what you might expect, which is, again, it's non-zero only at this sort of on the light cone. Okay, you see there's some populations inside, which is due to errors, and when we looked at this, we got hope, and I would say that this is kind of largest scale digital simulation of the correlation function at the time of publishing, right? And maybe somebody else can tell me that there's another calculation of a correlation function is for some interacting many-body system, which is important that they know about, but I hadn't seen that. So just a word, obviously what was really important for us was a good error mitigation strategy, and this is where the people in algorithmic really came in with their tensor network-based error mitigation strategy. So, I'm not no means an expert on that side of the coin, but just to tell you that, again, on this plot, you're at a non-Clifford dual unitary point, and as I've argued, it's known from theory what the decay of that correlation should be as a function of time and h, okay? So you're able to use this as a really good benchmark for your error mitigation strategy. So the error mitigation strategy that algorithmic typically employ is called TEM, okay? And the basic idea is that you need to do a lot of noise learning in between your gates. You try to construct a tensor network representation of your noise model and then apply the inverse map in post-processing to your data, okay? That's basically how the thing works. But you see that we were able to sort of revive this signal so that it lies on the theoretical prediction for that particular value of the H field. So that I've already said that, but you see it's a challenge, right? Because in some sense it's a bad choice of correlation function to do error mitigation on because it decays exponentially in time, right? The signal decays exponentially in time. So I mean, for larger values of H, this signal is rapidly decaying, and this is always the problem, right? So too high in H means the signal goes so low that you can't really revive it through error mitigation schemes anymore. But at least for some values of H, which are interesting, we were able to sort of do this type of a revival. And all of this sort of tensor network-based error mitigation from algorithmic, I promised them that I would tell you it's available up on the QSim functions now, so you can use it and play around with it if you like and want to use it in your own sort of simulations. So show you some more results. So this was the kind of full sort of setting. So what you see on the left-hand side is the Clifford point. This is when the transverse field is 0. It's predicted from theory that actually the autocorrelation function doesn't decay at all there, right? Because model is completely integrable. Autocorrelation function is 0, you see that the unmitigated data is decaying exponentially, okay, but the error mitigation brings it up to where it should be again, and that can be used for further benchmarking. And then as you go from sort of left to right, you see we turn on this transverse field, and the exponential decay gets faster and faster, okay? So we were able to go up, as I said, to around 91 qubit circuit. Notice that the prediction for the autocorrelation function, which comes from theory, is independent of the system size, which is also very good for benchmarking, okay? So what this allows you to do now is benchmark your error mitigation, okay? Sort of get everything working correctly, and then try to perturb away from Clifford and dual unitary points a little bit. This would be the kind of future goal of this type of a simulation. So just to see on the right-hand side, everything is kind of revived by error mitigation. Everything works very well. But say, for example, what we tried to do then, as I was saying, was to perturb away from the dual unitary point, really, to make something non-Clifford, non-integrable, and non-dual unitary using sort of using the benchmark as a sort of guiding star. Okay, that was the idea. So you see, now I just want to, this is a little bit confusing because what we're computing here is the expectation value of an observable, okay? Away from the dual unitary point, this has nothing to do with correlation functions, okay? So it just really gives you, it gives you an expectation value of sigma x somewhere on the circuit, right? It's only at the dual unitary point that you can interpret this as sort of correlation function. So what we use as a benchmark here is numerics, right? That's the best you can do, okay? And we were hopeful when we started out, rather naive. We thought that maybe this is a good place to look for something that's hard classically. It turns out that it's not, right? So it's hard in the Schrodinger picture because it's really entangling the circuit if you want to apply a tensor network. So you see that this sort of tensor network, vanilla tensor network based on the Schrodinger evolution sort of struggles. You have to use very high bond dimension because the circuit's so entangling. But of course, because of this very sort of restricted light cone structure, Heisenberg techniques work very well here, right? They converge perfectly. So it's not, we're not claiming anything. What I would say, and maybe I can sort of conclude with that, I'm a little bit early, I know, but is, just because something has an analytic solution, it doesn't mean that at finite system size, certain quantities can't be hard, right? So higher order correlation functions like the ones we heard about in the talk on Monday, like autox, higher order correlation functions here, can be difficult to simulate with numerical methods, and it's something that we're kind of actively working on at the moment, okay? So in summary, I hope that I've convinced you that this sort of story of discrete circuits can give rise to new emergent phases, right? That's kind of the idea of emergence, right? You start with something which is very simple rules, you scale up, right? And new physics, stuff that you wouldn't have expected occurs, right? You can't really tell what happens just from looking at the individual components, and I think dual unitary circuits are a very good sort of example of that. They also provide analytic benchmarks. Again, not everything can be computed analytically in a dual unitary circuit. Only certain things can be computed, like correlation functions, spectral form factors. If you want to know the details, fine. And what I'm saying is that the type of experiments that we did, they can in principle be extended on new devices with better coherence times to measure higher order correlation functions where you don't necessarily have this issue of having an exponentially decaying signal, right? You might have something more favorable that error mitigation can work on a little bit better. And yeah, so that's all I really wanted to talk about. I thank you all for your time.
Questions for John?